A mayor running for re-election claims that during his term, average municipal taxes have fallen by $250. A conscientious statistician wants to test this claim. She surveys 41 of her neighbors and finds that their taxes decreased in dollars as follows. And then we have the data. The statistician assumes a population standard deviation of $13. Do you think the statistician should reject the mayor's claim? Why or why not? So this problem is an introduction to hypothesis testing. It's not a full hypothesis test, but it starts to give us it starts to help us understand some of the main themes and ideas and how this all works. Okay? So step one here, we need to state the hypothesis. What's the claim that we're actually testing here? Okay? So we see the claim right away. A mayor running for re-election claims that during his term, average municipal taxes have fallen by $250. And then we could even see that that's what we're testing. A conscientious statistician wants to test this claim. So the first thing we need to do is we need to decide, is we testing a population proportion or a population mean? Well, we are talking about average municipal taxes, right? An average amount. Well, average is a different name for mean. So we are testing the mean, right? And in this case, the mayor is claiming that the average municipal taxes have fallen by $250. So average is $250. Okay, so that's our step one. That's the hypothesis that we're claiming. Have average municipal taxes actually fallen by $250 or have they not? Okay, so step two, now we want to determine the features of the distribution of point estimates using the central limit theorem. And we want to do this assuming this hypothesis is correct. Assuming this hypothesis is correct. Okay, so we're going to do this using the central limit theorem. And the first thing we are going to do is we're going to decide what kind of distribution we're dealing with. Are the point estimates here, which in this case would be our sample means, is the distribution of sample means, are they normally distributed or are they t-distributed? Well, for means, it depends on whether or not you know your population standard deviation. In this case, we are assuming that the population standard deviation is $13. Since we know the population standard deviation, we can use a normal distribution. Our sample means are normally distributed. Okay. Now, what is the distribution means of these sample means? What is the mean of all those means? Okay. Well, if you remember, the central limit theorem says that the distribution of all sample means, if we know the population standard deviation, is normally distributed with mean mu x bar, standard deviation sigma x bar, where mu x bar, the mean of this distribution of sample means, is just the same as the population mean. And sigma x bar is the same as the population standard deviation. Sometimes we call this sigma sub x. I'll just write it as sigma for now, divided by the square root of n, where n is the sample size. Okay? So part of what we're doing here is we are assuming that the population mean is 250. So that means the distribution mean of the distribution of sample means is also 250, right? Because that is what the central limit theorem tells us. And the standard deviation, that's the next thing we're finding, the distribution standard deviation is just the population standard deviation divided by the square root of the sample size. And we know that the population standard deviation is $13. So let's go to our notebook. Sigma sub x bar, so the standard deviation of our sample means, is our population standard deviation, $13, divided by the square root of the sample size. And in this case, the sample size is 41, right? We have 41 data points. You can count them if you want to, but it tells you right here in the problem. We have 41 data points. Okay, so that's going to give me my standard deviation of the distribution of my sample means. I'm going to type it one more time so I get it printed out. And there we go. Standard deviation is about 2.03. Okay, so now we know how it's distributed. And what this means, by the way, is for our particular problem, our sample means are normally distributed with mean 250, and distribution standard deviation about 2.03. Okay, so that's what it's telling us. Okay, so assuming the claim is true, find the probability of obtaining the point estimate. Okay, so in this case, we want to find the probability of that we have an X bar, a sample mean, that is at least as extreme of the sample mean we actually will get with this data. Okay, because we're trying to test the population. So we don't want a sample proportion, we want the sample mean. Okay. Next, we need to decide on an inequality symbol, and we need to decide on the boundary value. Okay. For these problems, you should find this boundary value first. It's going to make finding this inequality symbol much easier. Okay. So this boundary value should be the sample mean that we get from this sample, because we want to find the probability that sample means are more extreme than the sample mean we actually got. So this is the value at the boundary. So let me grab all this data. There. So I just copied and pasted it in here, so I have all the data in there, and I am ready to find the mean. So my n is however many values I have, so length of that list of values, length of x. And then my sample mean is just going to be the sum of all those values divided by n. Okay, and hopefully you're very comfortable with this. We've been finding means quite a bit throughout this course, so now this should be pretty familiar to you. And I'm going to type it one more time so it prints out. So the actual sample mean I have for this particular sample is about 248.24. So let's copy that. That's our boundary value there. Okay, so what's going on here? Okay, we know our sample means are normally distributed, right? So get that lovely bell curve with that normal distribution. Okay, and the mean is 250. Let me write that in black. The mean is 250. That's what we are assuming the population mean is. That's what our hypothesis says it is. That's what we're hypothesizing. But our sample mean, what we get when we actually get just a few of the people in the community, we get a sample mean of about $248. Now that's less than 250. That's over here somewhere. $248 and what was it? 24 cents. Okay. So we want to find the probability that we are more extreme than this sample mean. That's what our goal is, right? So notice that if I go with these values in the upper tail, there's a lot of values there that are not more extreme than 248.24. By more extreme, we mean further away from the mean. And all these values right here are actually closer to the mean of 250 than our 248.24, right? We want values that are farther away, that are more extreme. So that means we actually want this side of 248.24. We want to know the probability of that because all these values over here are further away from 250. They're more extreme. So we would be finding the probability that we are at least as extreme as 248.24. Okay, so with that in mind, let's go back and look what we have here. We still need that inequality symbol, right? Well, 248.24 is less than 250, and so we want the tail it's closer to. And we could see that we're getting the lower tail, which is the values smaller than 248.24. So we want less than or equal to. Okay? And then here, we want to convert that to a probability either using z-scores, using a standard normal distribution, or t-scores with a t-distribution. Now in this case, we already know that our distribution of sample means is normally distributed. And so we're going to convert to a standard normal distribution using z-scores. Okay? Now, we're going to have exactly the same inequality here as we had here. Okay? And what we're going to be doing is we're just going to find an equivalent probability using a standard normal distribution. To do that, we need to convert our sample mean into a z-score. Okay? So to convert to a z-score, remember a z-score is just the point estimate. So in this case, that would be our sample mean. Our sample mean is estimating the population mean, minus the mean of the distribution of point estimates, so the mean from our central limit theorem, divided by the standard deviation of our point estimates. Okay? So we have all those pieces. We have them right here, right? 250, that is our population mean. So remember, this guy is just the same as the population mean. And then 2.03, that's what we calculated before, and that will be our sigma x bar. So let's go ahead and find that z-score using our notebook. Okay. And so we'll have z, we'll have our sample mean, that's our point estimate, minus our population mean, right? Now, I don't have a variable for that yet. I could just type it in. I could just type in 250. I kind of like dealing with variables. It keeps things simpler for me. So I'm going to create another variable with that 250. Okay? Now, you don't have to. You could just copy and paste the numbers if you want. But I find it easier to read with the variables. Okay? So I have my point estimate minus my mean of the distribution of point estimates, mean of the distribution of sample means, divided by, and I do have my sigma x bar already. Sigma x bar. And so all this is doing is this is just computing this formula here. Okay, using the numbers for those values. Okay, and I'll just type that z one more time so we actually get the value. And so our z-score here is negative 0.86 about. So let's copy and paste that into where it goes. So what this is saying is the probability that a sample mean is more extreme than 248 if the population mean is 250. Remember, we don't know that, we're testing it. So if the population mean is 250, it would be the same as the probability that our z-score is less than or equal to negative 0.86. And that is a quantity we can easily compute using our notebook. We'll just use our p-norm function, plug in our z-score, and our lower tail will be true. In this case, our lower tail is shaded. Okay, run that, and we have our probability. So it's about 19%. Okay, so what's this saying? This is saying that if this hypothesis is true, then there is about a 19% chance that we get a sample like this with a sample mean at least as extreme as $248.24. So step 4, and for step 4 in this part, we're not, you don't actually have to answer anything, but you should think about it. What do you think? Based on the probability calculated in step 3, right here, of obtaining the point estimate, would you reject the claim? Well, there's about a 19% chance of getting a sample like this, or a sample with a sample mean more extreme than this one, if the population mean is actually $250. Well, 19%, that's actually not terribly unlikely. That's a fairly large probability. So if it were me, I'd say, you know what, that's not so unusual an event that I think that I could safely conclude this hypothesis that is incorrect. So I'm going to not be able to disprove this hypothesis. I'll have to kind of accept it for face value for now. I can't say that the mayor is lying. I cannot conclusively say that. Because, I got something that's a little lower, but not so much lower that we can safely conclude that the rest of the population is also lower. Okay. Now, later on in this chapter, we will be a little bit more careful about this. Right now, we're just kind of looking at this and feeling it out, and you have to make kind of a judgment call. Is 19% so unlikely that you think that our hypothesis here must be false? Or is 19% likely enough that we can't really conclude that this hypothesis is false, that it might very well be true? Okay. In this case, as I said, I think 19% is large enough that that the hypothesis could very well be true. There's a strong likelihood of it.